Hello. Welcome back to my channel. So this is part 2 of the spring semester review. Today we're going to cover Unit 8, Chemical Reactions. So as you can see here, it's kind of a heavy unit, not too long, but it does involve a lot of problem solving. So we're just going to go ahead and get started, and I already kind of had a head start. First we're going to cover balancing equations. And before we actually get into the practice of balancing, you have to know the concept of why we balance. And the concept of that is called law of conservation of mass. So what does that mean? Like, the definition literally means that matter cannot be created or destroyed. So in any chemical reaction, whatever goes in has to come out. So how much mass, for example, comes in equals the mass coming out. So just to put it in simpler terms, amounts going in equals going out. I like to put it in the fewest words possible. So, but the scientific definition is matter cannot be created or destroyed. So there's nothing extra and nothing gets left behind. Okay? So, for example, if I give a question regarding law of conservation of mass, for example, if I tell you, I lost my train of thought. How many, there we go, okay. How many oxygen atoms are produced if 5 oxygen atoms are used? So this is actually a very simple question. I'm putting stars because that means it's importance. Okay. When you read a full sentence like this, you're like, wait, what is it saying? So basically it's saying, if I have 5 oxygen atoms that are being used, how much should I have going out of the reaction? So with law of conservation of mass, amount going in equals amount going out. So literally 5 oxygen atoms are produced. That's it. It's easy yet so difficult. So it's all about understanding the concept. Okay? Which is why when we balance, both sides have to equal the same. Alright? So let's now get into the balancing. I'm going to do blanks as where we're going to put our coefficients. So when we balance, we only add coefficients. We never change the subscripts, okay? Because the thing is, when we trying to make a reaction balance, we add more things, like the whole compound. We don't change the actual, component of like the compound. Because if we change this H2O to HO, it's no longer water, So we'll just have to add another water, for example, if we need to balance the other side. Alright, so when we have a balanced equation like this, you should do inventory, basically just counting how many on each side. And the arrow here is basically our border, our split. So on the left side, I can see I have 2 hydrogens and I have 2 oxygens. And then on this side, I have 2 hydrogens and 1 oxygen. And from there we balance. And whenever we add a coefficient, it's going to affect the entire compound. So for now, hydrogen is balanced, so we're going to leave that alone. Oxygen, I have 2 here and 1 here, so I need to add something here to make this 2. And again, it gets to do with multiplication. So what times 1 equals 2? I'm going to put a 2 here, so basically I'm going to have 2 waters to try to balance out that oxygen. So now I have 2 oxygens. But as you can see here, that coefficient, it applies the entire compound. So 2 times 2, I have 4 hydrogens now. So now I have to go back and fix that hydrogen. All right, so now that oxygen's happy, I need to make hydrogen happy now. So what can I put here to make that 4? I could put 2. Now it's 4. Now everyone's happy. This is a balanced water reaction. So if this is blank, that means there's 1 O2. Okay, so you can leave this blank, or if it makes you feel better, you can put a 1. So these are the coefficients for this reaction. All right, let's do this one. All right. So we have more of a complicated reaction here. All right. So in this situation, so as you can see here, I started really simple. Here, there are polyatomics. There are compounds from the special list here. And when that's the case, when you can see on both sides, I would keep those polyatomics together. I like to say, like, keep them packaged, so that way it makes balancing a whole lot easier. If you see how we have NO3 on this side, NO3 on this side, I'm going to keep those together when I do my inventory. Otherwise, if I separate the nitrogen and the oxygen, say I have oxygen here, it's like the counting gets really difficult. So when I do my inventory, I like to do it in order. That makes it easier to balance. Honestly, you can balance however way you want, but if you do not like puzzles and you like to just balance boom, boom, boom quickly, I would suggest starting with metals first. So in this situation, it's K. And then after any metals that you use, so K, so potassium is the only metal that we have. The next thing to list is your polyatomics, so like from your special list. So I have NO3 and SO4. Again, if you see them on both sides, you keep them together. If you don't see them on both sides, let's say I have NO3 on the left and I have like N and O separately on the other side, that's when you separate it, okay? So I'm going to put NO3 next and SO4 next, okay? It doesn't matter which one comes first, as long as it's following the metal. And then last but not least, I have hydrogens left. So I'm actually going to add this little special note. So a good order to do inventory, whichever applies to your reaction, is metals, and then your polyatomics, and then your nonmetals, then your oxygen and hydrogen last. Okay, the reason why I like to keep oxygen and hydrogen last is because eventually it'll balance itself out once you balance the rest before it. Okay, however, sometimes you do need to balance them at the end, but it's really simple. All right, so and by nonmetals, nonmetals, it excludes oxygen and hydrogen. That's, again, they're their own thing. Nonmetals mean like chlorine, nitrogen, sulfur, carbon, that sort of thing. All right. So when we balance now, let's take actually inventory. That helps. So I have 1 K. I have 1 NO3. I have 1 SO4. And I have 2 hydrogen. The other side, I have 2 Ks, 1 NO3, 1 SO4, and 1 H. All right, so now we are going to balance, and I'm going to go down the list. So K, I have 1 going in, 2 going out, so I'm simply going to put a 2 to balance out that K. But that 2 automatically made my NO3 to 2. So K is happy, move on to the next one. NO3, I have 2 going in now and 1 going out. So I can put a 2 for NO3. So that makes my H to 2. And look at that. everything is balanced. So this is why I like to go through this order. All right. Let's do one more. Try to do this by yourself. Actually, you know what? I'm going to give you a combustion reaction. So this special type of reaction that we're going to talk about more in a second. Because they actually have a special order of balancing. So how do you know this is a combustion reaction? Is when you have CH, O2, CO2, and water. These four components make it a combustion. So once I talk about the types of reactions, this will make better sense. But a hydrocarbon is any type of CH. It could be CH4, it could be CH6, it could be C2H6. It does not matter. And then you have oxygen gas, so it has to be O2, and the products are always CO2 and water. So think of combustion meaning to combust. It means to burn. And when you need to burn something, you need oxygen gas. Okay? So the order of balancing is CHO. And again, you can balance however you want, but combustion, where it gets very frustrating if you don't do this order. But whatever works for you. So the first thing you should do is to double your hydrocarbon, whatever hydrocarbon that you have. And then you balance your C. Then you balance your H, and then you balance your O. Which is why I listed it like this. Okay? So carbon right now has 1, hydrogen has 4, and oxygen has 2 on the left side. On the other side, I have 1 carbon going out, 2 hydrogens going out, and then I have 1, 2, 3 oxygens going out. Alright, so now I'm going to balance. So even if carbon is already balanced here in combustion, always just double it so that way hydrogen and oxygen can easily get balanced. Okay, so I'm just going to put a 2 on CH4, so that changed my carbon to 2. My hydrogen is now 8, 2 times 4, 8. And that's pretty much it, what the 2 did. So I just did that first step. Alright, balancing my carbon, I'm going to put a 2 in front of CO2 to balance out my carbon to make that happy. But then again, it affects the entire side. So now that I put a 2 here, it affects the oxygen. Now don't forget about this oxygen. We need to recount the entire side. So we have 2 times 2 is 4, plus 1 is 5. So now we did that second step. Next step is balance the H. I have 8 going in. I need to put something here to make it 8 as well. So that would be 4. And then again, don't forget to recount the entire side of oxygen. So I have 4 oxygens plus 4 oxygens. That is 8. Now, last but not least, I gotta fill this in. What times 2 equals 8? 4. Now everyone's happy. However, can these coefficients be simplified? Absolutely. All of these can be simplified by dividing everything by 2. So 1, 2, 1, 2. Alright? On the exam, your coefficients will be simplified. So maybe you'll have something like this, and you get it 2, 4, 2, 4. You're like, okay, I balanced it, but I don't see that on my answer choice. Maybe because it's simplified. So double check that you simplify all your coefficients. And by the way, it has to be an all or nothing situation, okay? If one of the coefficients cannot be simplified, leave it alone, okay? So if I let's say I go back up here, I have 2, 1, 2, right? It can be simplified, right? So we don't touch these 2, right? We just leave it as is. Same thing for this equations. These 2, don't touch them because these 2 coefficients are 1 and it's already simplified. Okay? do one more, and then you're gonna try it by yourself. I'm gonna give you a combustion reaction. C2H6 plus O2. Alright, so pause the video, try to do the inventory and balance, and simplify if needed. Okay, so this should have been your final balancing. As you can see here, I did not simplify because that 7 right here cannot be simplified. Everything else needs to be left alone. But it's 2, 7, 4, 6. Alright, so that is balancing. Now we're going to talk about types of reactions, and we actually already talked about one of them. But there are 5 types of reactions. RxN means reactions. So for the first reaction, it is called synthesis. That's when you have two separate elements add up together to make a compound. So that's A plus B makes AB. So for example, if I give you Na plus Cl2 makes NaCl. And if I were to balance it, it would be like this. Alright? So that's synthesis. But then there's the other way around, where you start with a compound, breaks down to elements, so that's decomposition. So that's literally backwards. Compound breaks down to A plus B. So let's say I have water, H2O, breaks down to hydrogen and oxygen gas. Now, why am I doing Cl2, H2O2? Remember Brinkelhoff, so the 7 diatomics. And I'll actually do that right after the types of reactions. So any of these 7 elements stand alone, it is in 2. Naturally, it's bonded in pairs. Okay? The third reaction type is called single replacement. That's when you have an element and a compound added together. And basically the element replaces one element, so one single element gets replaced to make a new compound. So for example, if I have like Na plus KCl makes K plus NaCl. And then we have double replacement. That's when you have, so single, one element replaces, double means 2 elements replaced. So that's when you have 2 compounds. So as you can see, as I go down, it gets more complicated. But double replacement is when 2 compounds, they switch partners, they make 2 completely new compounds, like that. So this is like, I think we just did it. This would be an example of a double replacement. So just to rewrite that, KNO3 plus H2SO4 makes K2SO4 plus HNO3. Alright, last but not least, we've got combustion, and again, I just talked about that. It's always just CH plus O2. It doesn't matter what CH it is, CO2 and water. It has to have all 4 of these. It doesn't mean if you have like CO2 and water somewhere in the equation that it's combustion. No, it has to have all of these. Alright? So if I were to give you, like, let's just go back just to give you examples, just to go back to these equations. So we already discussed that this is a double replacement, it has a compound and compound. And then if we look at this reaction here, we have an element, and it makes one compound. So that would be a synthesis reaction. And then we talk about this is combustion, this is combustion. All right. Now, how do I know if something is a single replacement? That is my next topic in the list, and that is called activity series. And this is mainly just used for single replacement reaction. Now I'm going to abbreviate SR, single replacement reaction. Alright, so the activity series, it's this resource right here, which you get to use. So activity series, this ranking right here tells you how reactive these metals are that can happen in a single replacement reaction. So the higher the activity, the higher rank that it is on the list, the better it will to replace the element. So for example, let's actually look at this reaction right here. Right? So Na plus KCl, right? So metals switch with metals, non-metals switch with non-metals. So in this case, Na and K will have to switch, right? So always remember that, because if you think about, like, you're an iPhone user, right? You have your iPhone for many years and you need a new phone. Would you easily switch over to Android? No, you would just get a new iPhone, right? Because you're an iPhone user, you always use iPhone. Same thing with Android. You stick with your Android. If you need a new phone, you'll just, get a new Android. It's not very easy to switch what type of phone you have. So same thing here. Sodium is a metal, will always switch with another metal, okay? So when you look at this reaction here, you have to check your activity series whether this reaction works or not, all right? So I'm going to look, is sodium higher than potassium on the list? So as you can see here, potassium is actually number 2. It's very reactive, and sodium is down here. So in this situation, this would be no reaction. All right? That means, like, when you put sodium and potassium, like sodium in potassium chloride, nothing happens. There's no reaction at all. However, if you do it the other way around, like K plus NaCl, when you put potassium in salt, basically, you clearly see that potassium is stronger, is higher rank, higher active than sodium, then it replaces. So that's when sodium is kicked out and potassium takes its place, like so. So that is how you do a single replacement reaction and how to use your activity series. And actually at the same time right now we are predicting products. So after single replacement, I'm going to show you how to do predicting products for double replacement reaction. So let me give you one other example for single replacement. Let's say I give you zinc plus Cu, so copper sulfide. So zinc is a metal, copper is a metal. We're going to see if they switch. So is zinc higher on the activity series than copper? Zinc is here, copper is way down here. So yes, zinc is indeed higher up. It is able to replace. So copper is kicked out, and then you have zinc sulfide. Alright, so let's do double replacement. And this is where you gotta make sure you switch properly and do your charges. So I'll do one example and then I'll give you one to try by yourself. So for example, I'll give you alright, so notice how we have two compounds here. And again, metals switch with metals, non-metals switch with non-metals. So I'm just going to switch over Na and Ca. They're just going to switch here. So instead of Na with F, Na is going to be with I. Na, I. And don't carry any subscripts with you. That's the whole point of making the new compound, and then do charges and crisscross. Okay? Na with I, then Ca with F. Again, metals come first. Don't do F and then Ca. That just looks wrong. So metal and then non-metal. And now you do charges. So again, you should know your charges by now. So Na is a +1 charge. Iodine is a -1 charge. So that cancels out. Calcium has a +2 charge, hence why that 2 was there. So the 2 goes here. And then fluorine has a -1 charge, so that doesn't matter. But that is pretty much it with predicting products of double replacement. And I don't think for your exam you're going to have to balance this, just predicting products. Balancing is balancing, predicting products is just predicting products. Okay? Let me give you one more. Try by yourself. So this time it has the special list, so again, they stay together. So go ahead and try it, pause the video, and then check your work once you're done. Alright, so you should have gotten these as your products. K goes with OH, and they both have a 1 charge, so they cancel out. Ca goes with NO3, and then since Ca has a +2 charge, the 2 goes after the NO3. Alright, and that is pretty much the end of this unit. It's kind of a lot, but it's just a lot of practice basically. But that is Unit 8. That is chemical reactions for you. Just I would really understand your types of reactions and then the concept of switching and predicting the products. So again, all of this is going to be on the final. Definitely know your balancing, know your rules. The tip that I would give you, since like multiple choice, if you don't have time to fully balance and stuff, with the multiple choice answers, maybe put in those possible answer choices and see that it balances both sides. Okay? So yeah, I hope this helps. Let me know if you have any questions. Have a great day.